discussion leader.
Oh, yeah.
All right. So, as we begin our time together, I want to talk a little bit about how this class is going to be structured over the next couple of weeks. So this week, this chapter is packed with a lot of information. And so this week, I know how much you love our discussion Fridays. This Friday, we're going to have to shorten our discussion Friday because we're going to be finishing up covering material from chapter 29. So that's kind of an FYI of what's going to come on Friday. Next Friday, we're not going to have a discussion Friday at all because we're going to have exam Friday. Okay, so exam 3, I was right when I said I believe exam 3 is 2 weeks from today. When I said that on Friday, I was right. So our exam is next Friday. So also something you can expect is over this weekend, hopefully close to Friday, is you will get a study guide for exam 3. And again, as a reminder, I said this on Friday as I handed back the exam. Anybody who got less than 120 on the previous exam, I want to see your study guide before. And by see it, and again, I told you this on Friday, but if you don't want to sit down and go through it together, that's fine. But I want to see your study guide so I can make suggestions on where you may be missing some bits of information. Some of you have already done homework 10, and so you've noticed this, but just kind of a heads up, as you go through and you do the second portion of your homework 10, sometime between Wednesday and Sunday, or you could even do it earlier if you want, you actually have to point out something in somebody's response that you don't agree with and actually give maybe some rationale as far as why you don't agree with it. So it may take you some added requirements as far as getting in and reading through people's posts more carefully, and then also studying the material a little bit more as well. And if it gets to a point where if, I'll look through it as everybody's posted their response, if there's literally not a single person in there that puts something that it's not possible for you to disagree with it, I will make a post where I will have some information in there that you ought to disagree with. All right? And it's not going to be super obvious which bits of those informations you should disagree with unless you have worked through the material and you know it well. All right? Yeah. They shouldn't be. So there should be a couple of groups of 6 that can take a 7th. Any groups of 6 out there that can take a 7th?
Where are you at though?
Okay, well, so you can form another group, just a smaller group, or you can jump into a group of 7. That's fine, and have a couple of groups of 8. That'll work as well. All right. So that's what to expect over the next couple of weeks. I believe this is this week 11? Or it's week 10? Okay, so I got a little bit carried away thinking about the exam that we're going to have next week. But it's week 10, so we're getting towards the end of our time together, which is sad for me, probably very exciting for you, provides a great deal of hope. But then for those of you that are going to be taking cell biology, I teach that as well, and we just get to do part 2, right? The sequel. But in this case, the sequel arguably is actually better than the original because there are a lot of really cool things we get to talk about in cell that we don't have an opportunity to talk about here. All right. So there's what to expect over the next couple of weeks. We're in our groups of 6/7/8. You all have hopefully a discussion leader that's going to get everybody engaged as we work through this because we're talking about vertebrates. We are vertebrates. And so this is a group of animals that we know the most about. Meaning, this is a group of animals that we get most opportunity to have some really meaningful discussions. All right? Somebody pray for us, please. I don't want to pray for us. I mean, I do, but I would rather somebody else. Well, we had Joey's hand went up first. So, Jack, you can pray for us on Wednesday. Joey.
Dear God, I thank you for this morning. I thank you for the rainy weather. It smells really nice outside. And I pray that we would learn this morning, that we would apply ourselves, and that would glorify you, and that we would have a good time doing it. In Jesus' name, amen.
All right. Here are the framing questions. And up to this point, I think the most framing questions we've ever had from a chapter was 7. And usually it's 6. And here I think there are 9. I don't count very well because I'm very lazy and I just kind of work through things quickly, but I'm pretty sure there are 9. And I don't think we've ever gotten through more than 4 in one day, and we didn't even finish that 4th. And so usually we go through 3 in a day, which would basically make us finish up on Friday talking about this, which is why I said, our normal discussion Friday may not be so normal this week. But don't worry, we'll still have a quiz. So don't worry. Don't be afraid about that. All right, so these first 3 framing questions, if we get through them, we will start on the 4th. But the first 3, do all chordates really have the 4 hallmark features? I introduced these 4 features on Wednesday. We'll kind of hit these again and talk about when do you see them, how do you see them. Which came first, the cranium or the vertebral column? This is kind of a fun question to deal with. And then lastly, why are gnathostomes favored? Yeah, this is fun. I'm going to have a lot of fun today. I hope you will as well. Join me, right, in the excitement. Otherwise, it's just awkward. If I'm having fun and you all are miserable, then I feel... Actually, I was going to say I feel horrible, but I don't. And I do feel a little awkward, but that's okay, because, I'm a biologist, right? I feel awkward all the time. All right, do all chordates really have the 4 hallmark features? And the simple answer to this is at least at some point in development. At least at some point in development. So there are many of these organisms in this phylum, in phylum Chordata, where you, for most of the life cycle of the organism, you do not see some of those hallmark features. So it gets a little weird. But at least at some point in development, you do see these 4 hallmark features. And so let's talk about the 3 varieties or 3 subphyla that we can split phylum Chordata or chordates into. So they come in 3 varieties, which are 3 subphyla. First one, Urochordates, or Urochordata, sometimes called tunicates, sometimes called sea squirts. So if you've spent a lot of time in intertidal areas or in shallow marine environments, you may have seen these referred to as sea squirts. These are these organisms. And so these go through, like echinoderms do, a very complex metamorphosis. So the tunicate or the Urochordate larva very characteristically have the 4 hallmark features. But as they go through this complex metamorphosis to become adults, they lose 3 of those 4 hallmark features. They lose the notochord, they lose the postanal tail, and they lose the dorsal hollow nerve cord. And the thing about this, so let's talk a little bit about these features. The 4th one hasn't appeared yet. It will in the next point. But I want to talk a little bit about these because all we did on Wednesday was point these out and said, these are 4 features of chordates. All right? So the notochord, you may notice that cord, that is the same basically root as the phylum name. That's where the phylum gets its name. Chordata is the presence of the notochord. So the notochord is a skeletal rod. It's not compressible, so it's not fluid filled per se, although it kind of varies in how it's structured. But it's not compressible, but it's flexible. So it's a nice place where a lot of muscles can attach to, and as those muscles contract, which is what muscles do, it doesn't shorten the rod. The rod just bends. And so it provides a nice skeletal rod to build a body around. Postanal tail, this one should be obvious. It's a tail that extends beyond the anus. Dorsal hollow nerve cord. This is interesting because animals that have complex nervous systems, which chordates are not the only animals with complex nervous systems, right? We talked about this on Friday, I think. Yeah, we talked about it on Friday and we talked about it again on Wednesday. Complex nervous systems go along with bilateral symmetry, right? You get cephalization defining a head region with bilateral symmetry. You also get complex nervous systems. But having it on the dorsal surface, which is on the back, is unique to chordates. Okay? Other animals have complex nervous systems, but they have their major nerve cord run along the ventral surface, which is the surface along the ground. All right, so those are urochordates. So as they go through that metamorphosis, they lose 3 of the features. Cephalochordates, also referred to as lancelets. These are filter feeders, which adult urochordates are also filter feeders. These are filter feeders, and they have all 4 of the hallmark characteristics. So we still haven't mentioned the fourth again. And if you don't remember back to Wednesday when we gave you the list, you're hungry, right? You're like, what is that fourth characteristic? I get it, because I'm there with you, right? I'm waiting and I know what's coming. What's the fourth hallmark characteristic? Here it is. So craniates, this is the last of the three subphyla that we can split chordata into, and this includes us. And we usually do not retain the notochord. It gets replaced by something else. In us, it gets replaced by the vertebral column, and in most craniates, it gets replaced by the vertebral column as well. And we usually do not retain the pharyngeal slits, the last of the four hallmark chordate characteristics. Pharyngeal slits, which work really nicely for filter feeding, right? You've got slits in your pharynx, which our pharynx is really reduced, but anyways, so it's nice drawing fluid in the mouth and then forcing water out through the pharyngeal slits, and then material in those slits trap whatever is in the water. Works really nice for filter feeding. Does not work so nicely for trying to swallow an animal whole, right? To have these pharyngeal slits. It doesn't also work well for like chewing and making that bolus like we do and then swallowing a large amount of material. So during development, you can see pharyngeal slits in human development, and then they develop into various structures in a juvenile and then adult human. Yeah. So some argue, and I think extremely well, for actually having a fifth hallmark characteristic. And this is present in all of these chordates, and it's the endostyle / thyroid gland. And so it comes in a couple of different varieties, but it's basically a structure that's involved in iodine metabolism and metabolizing it for various purposes. So sometimes you interact with that. The textbook doesn't talk at all about this, but I know what's going to happen because you, in an effort to be able to point out something that's incorrect in somebody's response because you feel compelled to do so, you're going to do an extremely large amount of additional research and preparation for it. I know exactly that's what's going to happen. And I think sometimes you'll come across that there are 5 hallmark characteristics of a chordate, and I don't want you to be confused, having never been introduced to this, and then become angry with me for not actually telling you about this 5th characteristic. Because I get it. That can happen. All right. Any questions about this question? So do they all really have the full hallmark characteristics? The answer is yes. Yes, they do, just not at all points or all stages or all portions of development. And there's also a 5th characteristic that they all have, an endostyle / thyroid gland.
Is the 5th characteristic, do they have that at all points of their existence?
So the endostyle thyroid gland, it's present all the time in adults and even in adult tunicates, in larval tunicates, in cephalochordates.
So why is that kind of like the unknown?
Oh, because it's been a more recent discovery. Yeah, not its presence, but its presence in all groups. And so textbook authors don't always include it because it's not part of like the original lists. So the original lists date back, 200 years.
But the original list, it's like, it has this at some point
Mm-hmm.
in their life and development, whereas the 5th characteristic, they have it at all points.
Yeah, but sometimes it changes form from endostyle to thyroid gland, so it gets a little bit complex. Yeah, Joey.
So even though like we don't have the pharyngeal slits anymore, we have them during development.
Yes. Mm-hmm.
Okay.
Yep, and you can see at a point in development where there are all those pharyngeal slits. Then now they don't go all the way through; they're more like pouches. But you see them very clearly, and then they go into develop various structures. Some of them skeletal elements, some of them other structures. Yeah.
Is the endostyle and thyroid, are those 2 different things?
It's
or are
basically
those
2 different
variations?
varieties
Okay.
of the same thing.
Got it. So 2
Yeah.
different forms. Okay.
Yeah. That's a good question. All right. Everybody's favorite thing in the whole wide world. Here we have a phylogeny of this, of all deuterostomes, actually. So all deuterostomes, and so if you wanted to put a couple of things here that were characteristic of all deuterostomes, you could reflect back to our time on Friday, and you'd have a wonderful list. I just realized right now I didn't bring my computer on Friday, so I didn't record that discussion. Oh. If you weren't here and part of that, you need to get the results of that, because that was awesome. We had a great time together. I had a wonderful time, and I think most of the people in here had an okay time, so it wasn't a super awkward day. And so here we have chordates just representing this branch, and notice of our non-vertebrate chordates, our other subphyla, which one is grouped closer to the craniates, to the vertebrates? Urochordata or Cephalochordata? So Cephalochordata is here, and then Urochordata is here, grouping closer to the rest of our chordates than Cephalochordata is, right? Keep that in mind, because the textbook is extremely inconsistent with which one of those subphyla group closest with the craniates. And it's an important distinction and something that we'll actually talk a lot about, because what you should actually have here, let me ask you this, and then somebody's going to give me the answer for what we should have here. You ready? This is going to be exciting. Okay. If there's inconsistencies as far as which group is closer to which, it's probably an indication that rather than having a clean phylogeny, you have what?
A polytomy.
Yes! What's actually, sorry, I got really excited there, but that was fun. What this should have is you should have a polytomy with Cephalochordata, Urochordata, and craniates all coming from a single branch. Thank you. That was nice. I love the visual effects. Yeah.
That was auditory.
Oh, man. But I saw you do it, right? I saw you. Gosh, you're right. You're right. You deserve better. I'm sorry. All right. So here are the 4 characteristics pointed out. You've got your dorsal hollow nerve cord on the dorsal surface. You've got your notochord, that skeletal rod. It's not compressible, but it's flexible. And so it's a great thing to attach muscles to create some real dynamic movement. You've got your postanal tail. You've got your pharyngeal slits, your 4 hallmark characteristics.
This is a Lancelot?
It would be, this is a representation of the original chordate ancestor, a cartoon of it. But yeah, the lanceolets, maybe. But the lanceolets look a lot like, it's just a cartoon representation summing up all. Yeah. So here is a representation of what happens in urochordates. Again, they go through a complex metamorphosis like echinoderms. And when they do, they forsake some of the characteristics that are nice for bilateral symmetry and really dynamic movement. Okay? So they forsake the notochord, they forsake the postanal tail, they forsake the dorsal hollow nerve cord, and if they get rid of their nerve cord, what do you imagine they also get rid of? If they got rid of a big chunk of their nervous system, what do you think they also get rid of? Their head, their cephalization, and they actually take on a radial symmetry, like an echinoderm does. Here's a lancelet, a cephalochordate. Again, yeah, I mean, very, very characteristic of chordates. And so this is why it's nice to think that this is the most primitive, and that's what that phylogeny represented, right? Cephalochordates and then urochordates being closer to the craniates, right? But you got some problems there because we're more genetically similar to cephalochordates than we are to urochordates. But urochordates have a feature that we have that cephalochordates do not. And cephalochordates just, I mean, they're just perfect. They're like textbook of what a simple chordate should look like. And so again, we should have a polytomy. It's just a mess. It's just a great big old mess. 1 branch into 3. I guess that's not a horrible mess because 1 branch into 3 is better than 1 branch into 5, right? Or 7, or 34. We'll get into some of those polytomies. Those are fun. To be continued. All right. Which came first, the cranium or the vertebral column? The cranium or the vertebral column? Yeah, and that's the simple answer. The cranium would have had to come first if we root these all back to a single ancestor. But man, you just spoiled my whole slide. But that's okay. We'll get there. We got to get all the steps even though you know the end, right? It's like watching the movie before you read the book, right? You already know how it's going to end, but then you read the book and you're like, wow, they left out so many important details. I feel like I was cheated in that movie experience. Phylum Chordata has both invertebrates and vertebrates, so keep that in mind. It's kind of just an interesting phenomenon that you have a single phylum that has both vertebrates and invertebrates. Now, traditionally, hagfish, which is a living group, the class is Myxini, were grouped in with vertebrates. So we had basically 3 subphyla. We had, bless you, we had Cephalochordata, the lanceolets, we had Urochordata, the tunicates or sea squirts, and then we had Vertebrata, the vertebrates. But here's the problem. Hagfish retain their notochord. It never gets replaced with the vertebral column. So now you have a whole group of organisms, the hagfish, which you're like, I know what you're thinking. You're like, there are only 20 species of hagfish. Is it really that big of a deal? Well, yeah, it is. Anyways, we can have that discussion, later if you're really troubled about it. Hagfish retain their notochord. They never develop vertebrae. So you've then got a group of vertebrates that don't have vertebrae. And that makes people uncomfortable. I don't know why. But it makes people uncomfortable. However, they do have a cranium. So they've got that cephalization that comes along with bilateral symmetry. Because they are a chordate, their brain is just, it's bigger on average than other animal brains. And so they have a really robust structure to protect that brain, the cranium. And so now what you have is you still have 3 subphyla. You have Cephalochordata, you have Urochordata, and then you have Craniata. So subphylum Craniata unites hagfish with all of the vertebrates. Unites hagfish with all of the vertebrates. And so basically what you get from this, that we have a group of living craniates that don't have vertebrae, and then you've got all these groups of living vertebrates. If all of these groups do root back to a single ancestor, it indicates that the cranium actually came about before the vertebral column. So the cranium developed around the anterior-most, or the very beginning of that dorsal hollow nerve cord. The cranium develops around that, and then as this organism continues to develop, continues to evolve, you replace the notochord, this skeletal rod that's protecting the dorsal hollow nerve cord, with vertebrae that actually protect it even better. Protect it even better. All right?
So what are the exact differences between a notochord and a vertebrate?
Save that question for our time of discussion, because that's exactly what we're going to talk about during our lecture break time. So save that question. Store it up. So you have a question that comes out of this, and again, the textbook is very inconsistent with this. Is the jaw part of the cranium or not? Because what's interesting is hagfish have a cranium but no vertebrae, right? So if you ever ask a question about hagfish, and I say, I don't know, hypothetically, why are hagfish so strange? And you'll be like, well, they have all the characteristics of vertebrates except vertebrae, which is kind of unfortunate because that's what the group is named after. But they have a cranium, right? And you're like, well, that's what's kind of strange and unique and cool about hagfish. And then you also talk about that they're scavengers and they help clean up whale carcasses that are sitting at the bottom of the ocean, so they don't just sit there and look gross. Hagfish take care of that. But then, you'll immediately go to, well, now we've got something interesting, and we'll talk about this more in the next slide, is that hagfish are jawless, and yet the textbook says the jaw is actually part of the cranium, that craniates have jaws, and yet you have craniates with no jaws. It's kind of interesting. So then it's like, well, are they ancestrally jawless, or are they derived? And we'll get there. We'll deal with that. All right. So here's our lecture break questions. Lecture break question, not questions. So if the notochord is a structural rod, why would it need to be replaced by vertebrae in some forms? And then part of this question comes what Charles asked, what is the difference between vertebrae and a notochord? The only thing you have for me so far is I said in some forms they develop vertebrae which protect it even better, right? That's all you have from me so far. So some of it you're going to have to pull from various things of just kind of thinking through, and then you can think about biomechanics of having vertebrae versus a single skeletal rod. But this, as discussion leaders, it's your responsibility to make this be fruitful and make sure every voice is heard, right? And then also, please, discussion leaders, find somebody in your group willing to share your group's ideas with the class as a whole, and don't force somebody to do it. Okay, that is not a good leader. All right? If you can't find somebody to volunteer, do it yourself as the leader and take the shame associated with not doing your job, but do it so that the job gets done. All right? Have at it. You've got 3 minutes to work this out.
Okay, guys.
My first thought would be like the bigger that an organism gets, they would need something stronger to support the extra mass, because if it's too flexible, then it wouldn't be able to, like, for us, it wouldn't be able to stand upright.
So basically, the notochord was inadequate as an organism, became bigger and more complex.
For upright walkers.
Well, uprightness.
Yeah, for uprightness. Yeah. Yeah, but for a bigger organism, too, like structurally, the notochord probably would not have been able to handle like complex movement, all that,
Yeah, it's kind
like
of
fish or anything like that. Like, because they need to be able to move in the water and change direction rapidly. And with the notochord, since you can't really bend it all that well, you can't do it. Whereas with vertebrates, it's individual segments. So the vertebrate is a segmentation where it allows it to turn and do different things, be more flexible in movement patterns.
Anybody have any idea over here?
The idea is that
That is
notochord is.
that the original notochords were inadequate as organisms evolved. Okay. Alright.
Also going along with that, one way they're different is with the flexibility. You have not calcium. I can't even think. Oh my gosh. You have to do it in between the vertebrates, which allows compression and stuff like that.
Yeah,
so it's not just,
like the liquid
Yeah.
fluid that's in between.
yeah, so it allows for
Compression.
more flexibility
Yeah.
and stuff like that too. So it's not just
30 seconds. Discussion leaders, every voice is heard.
So who would like to say this out loud? Who would like to talk? Anybody volunteer before I actually ask? No, if you don't want to, I can't force you.
nobody. If nobody will, then I will.
Okay. Oh, you have a thought. Okay.
I'm having a thought.
All right.
The
Throw it out.
trade-off between strength and flexibility has to do with it's more flexible and it's stronger. It still like reinforces the spinal cord and pushing
I couldn't hear everything. Can you say that again?
trade-off between strength and flexibility is exhibited in the vertebrae being replaced by vertebrae because the notochord is more flexible, but it's significantly weaker.
Okay.
Whereas this is stronger, but it's not as flexible.
So basically,
And
when
thus better reinforces.
okay, so basically, you lost flexibility when the vertebrate column
Yeah.
replaced the notochord.
All right. Okay. Okay. All right. So, we're going to start with this group over here. What do you got for us?
That when you have vertebrae, you kind of have more protection of the spinal cord, so the nervous system, as opposed to two separate structures running parallel to each other.
Right. So, yeah, that's good. I'm glad you picked up on that from either what you knew or from the drawing. So, the notochord, if you notice in like our cartoon, it just runs sort of parallel with the hollow nerve cord. It doesn't actually surround it and provide it any kind of encasing. Okay? It functions as a skeletal rod. Well, that's nice. And so if you were just replacing the notochord's ability to be a point of muscle attachment and to act as a skeletal rod, we'd have a much different question, right? So you're also adding some function that you didn't have before. And so the vertebrae add something that the notochord could not provide, and that's some actual encirclement, some protection, more than just support, also some protection of that hollow nerve cord that you didn't get out of the notochord. Love it. Group in the back.
Ours was pretty similar. The vertebrae is more complex than the notochord, so maybe it allows the nervous system to be more complex.
Potentially, yeah, it does certainly. It eliminates kind of some of the fragility of the nervous system, and so with that comes the potential to maybe have it be a more integrated, play a more integrated role, right, in what the organism can do. And you certainly do see a relationship between the presence of vertebrae and the complexity of the nervous system. Is having more complex skeletal rod, having the vertebrae cause the added nervous system complexity? I don't know, but there's certainly a correlation that when you have vertebrae, you have organisms with more complex nervous systems. Yeah, good. This group right here. Is this one group right here in the middle? Okay.
We kind of discussed a lot of what they said, but we also said, because when we talked about the notochord, it's not as compressible.
Uh-huh.
So maybe the vertebrae is more compressible.
Yeah, and so the vertebrae is just a completely different design altogether, right? And so, yeah, some of it, it's like, we need to replace this function of providing a skeletal rod, right? Part of it's adding a whole new function, right, of protecting the nerve cord. And that you do find a relationship between the complexity of the nervous system and the presence of vertebrae. But maybe something we're also you're kind of dealing with is part of this completely different design. You have basically alternating bone cartilaginous structure, bone cartilaginous structure as you look at least a human vertebral column. And so you do actually get some nice compressibility. Yeah, it's just a completely different design, right? It's not like a small tweak of an already present design. It's a completely different idea of how to make a skeletal rod. Completely different idea. And I heard up here, here, I'll let you all speak for yourself, and then, yeah.
All right.
Jackie, you're taking it? Okay.
So we kind of just discussed how vertebrae allow for a better mobility and flexibility of the organism, allowing it to perform more complex movements than if it just had a notochord.
Yeah, so even if there's flexibility in a rod, right? I mean, think about like a branch from a tree, right? That you've taken down so you could smack your siblings with it, right? And so there's some nice flexibility there. But when you have something that's built of all of these interlocking pieces, again, it's just a completely different way of coming at this issue. And you do get some added flexibility, and you get a lot higher control of that flexibility. I mean, think about a branch, as you go to bend it, it's a little bit difficult to control where that bend happens, right? It's like you may want it to happen at the very end, but it just kind of happens where it happens, right? But if you have all these different interlocking pieces, it's a lot easier to control where that flex actually happens. Where that flex actually happens. So you do actually get some added flexibility. And I heard something mentioned up here, the trade-off between strength and flexibility. There's no doubt that as a structure becomes more flexible, you lose some of the strength. The way around that is to come up with a completely novel design, right? So if all you did was made a more flexible notochord, then absolutely you're going to have a weaker notochord, right? If that's what you were doing, you're like, okay, we need to add some flexibility. We're just going to modify the notochord to make it more flexible. If you were to do that, you would lose some of the strength, no doubt. But coming up with a completely different design basically allows you to start from the ground and to say, we're just going to come about this in a completely different way. And then so the nice thing about the vertebral column is at the same time as it provides you greater flexibility, it also provides greater strength. Because it just basically came at this issue of providing the skeletal rod in a completely different way. Yeah.
So if humans had a notochord instead of vertebra,
Yeah.
then would we all be lame?
I don't know. I don't know. That'd be interesting. So the only living craniates that we have that have a notochord into adulthood are hagfish. And hagfish are super flexible. I mean, they can tie their whole bodies into a knot. And so, you're like, wow, that's really flexible. And then you're like, well, why can't we do that if a vertebral column is more flexible than a notochord? And the thing is, we've got other things limiting our mobility. It's not just our vertebral column limiting our mobility, but also the way our vertebral column is constructed, it's emphasizing strength over flexibility. So compared to other animals with vertebrae, we have less flexibility in our vertebral column and more strength, that trade-off of strength and flexibility. A cat's vertebral column is much more flexible than ours, but it's a lot weaker, okay, because there's a trade-off between strength and flexibility. Yeah, Joe.
So, are you saying it's not as simple as it sounds to say that vertebrae develop from a notochord?
They don't develop from a notochord. They develop and replace the notochord. So what happens is when you see an organism developing that has a notochord, which we do early in development, as soon as the vertebrae start to develop, the notochord starts to get resorbed. So it doesn't develop from the notochord. It develops basically where the notochord is, and then the notochord gets resorbed. It replaces the notochord. It doesn't necessarily come from the notochord. But you're thinking more of like a phylogenetic idea, I think, rather than an ontogenetic one. Ontogenetic would be developmental, right? Like, so if the vertebral column developed from the notochord, but if you're dealing with like a phylogenetic, talking about evolutionary history, you'd have to come up with, because it's basically a novel way of dealing with the problem, the way it develops is completely different. Meaning you're going to have to evolve a mechanism by which you develop something new and not evolve a structure from another structure. You're developing something entirely new.
Which, isn't that kind of harder?
Possibly. I mean, let's just say this. Yes, but it's not quite that simple.
Okay.
Yeah, it's not quite that simple because something else actually comes once you start to develop vertebrae. You start to develop something else as well, and then these living hagfish and lampreys, they just really make everything confusing. And we'll talk more about that in the next framing question. Yeah, Jack.
So with a lot of organisms that have the vertebral column,
Yep,
would you
yep.
say then that the notochord is like a placeholder then during development for
Sure.
the vertebral
Yeah,
column? Okay.
like a signal of where to develop.
Yeah.
Yeah.
And so for how many, like, what is the ratio of organisms and stuff that do retain their notochord up until?
So there are 20 living species of hagfish.
Okay.
There are about 50,000 species of craniates.
Okay.
Okay.
Got it.
So hagfish are 20 species
Yeah.
out of about 50,000. I don't know what that percentage is, but it's small.
Yeah. So
Right.
So.
So
basically-
what would 500 out of 50,000 would be 1%, and so 20 is 0.5% of 500. I
Okay.
think. No. Be 0.4. I don't know. Yeah, it's a really small percentage.
Okay.
So the overwhelming majority, well over 99% of all craniates, have vertebrae.
Got it.
Now they're not all made of bone. Some vertebrates have vertebrae made of cartilage, entirely of cartilage, cartilaginous blocks. But well over 99% of them have vertebrae.
So then would it be safe then to assume that maybe the notochord is just like an area during development in which it signals where the vertebrate column needs to develop?
Sure.
Okay.
Although you have like lancelets
Yeah.
and hagfish that don't develop it, and the idea is that that's the primitive condition. So then it's more than just providing a place for the vertebral column to develop because it can function without a vertebral column as a skeletal rod. Yeah.
So, as evolutionarily,
Uh-huh.
as the spinal cord developed, it did
Yep.
not.
Well, the
develop
spinal cord's
from
already there. You're talking spinal column.
spinal column.
Yeah.
So the notochord became the spinal cord.
No. So notochord is spinal column. Spinal cord is that dorsal hollow nerve cord. So the spinal cord and the spinal column and the vertebral column. So and again, you can't really say that the notochord becomes this because this develops completely separate, and then the notochord ceases to function. It's no longer needed and gets resorbed.
So what we have in our backs developed independently from the notochord, and it replaced the notochord. basically.
Yes.
Okay.
Yep. Yeah. All right. So again, here's kind of this inconsistency in what's presented in the text. So the idea there again, hagfish do not have vertebrae, right? Which is unfortunate if you're going to classify them as a vertebrate. And so now we classify them as a craniate. They do have a cranium, but the textbook presents this. So here we have an extinct fish, Dunkleosteus is the genus, and it's characterized by the presence of a cranium. So craniata, right, this subphylum, including this fish, is characterized by the presence of a cranium, a mandible being the jaw, and other facial bones. The problem is many of our craniates do not have a jaw, they do not have a mandible, and they don't have bone at all. And so now it's kind of interesting. So are craniates really characterized by the presence of a cranium, a mandible, and other facial bones? And you'd have to answer that question as no, they are not, but they are characterized by the presence of a cranium. So it's kind of just a complex story. Here's a great example of vertebrae. So we've got this group vertebrata, characterized by the presence of a backbone, a skeletal rod made up of cartilage or bone. Now, in almost all the species, it's made of bone, but you would have to assume that that's kind of a derived condition. All right. Our last question, why are gnathostomes favored? Why are gnathostomes favored? You're like, I have no idea what a gnathostome is, and I do not favor it in any way. Right? Yeah. Like, yeah, it just, I don't like something that I don't know what it is, right? It's what keeps us from trying something new. Luckily for me, I do not fear things I don't know what they are. I'm intrigued by them, right? And so I get to have lots of adventures in life, right? You go to a foreign country and the people you're there with say, don't eat the street food because you'll get sick. And I'm like, no, I want to experience what this country is all about. Not only am I going to eat the street food, but I'm going to eat an obnoxious amount of it because that's what I do as an American. So, sorry. That's another story for another time. Trips to Central America. All right. Anyways, so why are gnathostomes favored? So, first thing you need to know is many extinct and living craniates are jawless. Okay, we call these the agnathans. A meaning without, and or none, and gnatho or gnatha meaning jaw. So these are jawless groups. So many living and extinct craniates are jawless. Hagfish, what's that?
Is that Latin or Greek, the Gnathan?
That is a good question. I think it's Greek, but I don't know. I don't know for sure. Does anybody know Latin in here? Yeah, I think it's Greek, but I don't know. So hagfish and lamprey. Lamprey is class Petromyzontidae. Actually, that's a family. Petromyzontida is the class. These are the only living jawless craniates. Okay, are hagfish and lamprey. There are about 20 species of hagfishes, and as I said in the previous slide, they are scavengers, and they are benthic scavengers, meaning they feed along the bottom of the water column. They feed along the ocean floor. And so if you want to go on YouTube and find a video of a hagfish, you absolutely can. You might find a video of somebody trying to grab a hagfish, and they tie their body in a knot and secrete this nasty slime and, shoot their way out of the person's hand. Or you'll find a video of them just going to town on a whale carcass, and there'll be thousands of them.
And if you want
It's
a
really
lot of
interesting.
fun, look up the hagfish spill that happened in Oregon.
Hagfish spill. All right, and then there are about 40 living species of lampreys. These are filter feeders as larvae, and then as adults, they either don't feed, that is, the adult portion is very short-lived, or they're parasitic. They just kind of ride on the side of a fish, sucking nutrients from that fish. Very obvious parasitic lifestyle. A lot of lamprey will live basically their entire life as larvae, 7, 12 years as larvae, metamorph into adults just to reproduce and never feed, and then die.
For the parasitic ones, how long is the adult?
Yeah, they can. The adults of parasitic lamprey can live for much longer than the non-feeding. I don't know what the greatest lifespan is.
Is the lifespan how long?
The total lifespan?
Larvae versus adult.
Yeah, so the parasitic forms spend less time as larvae. They develop more rapidly, and they spend most of their life cycle as adults. Yeah. So then we have this extinct group of jawless fishes, the ostracoderms, and these are really interesting because these also lack jaws, but they have bone in their scales and have this bony armor that surrounds the entire animal. And so they're not obviously not fast swimmers because they just have this massive exoskeleton weighing them down. But now it's like, now we've got a problem here because they have bone. And this is a really primitive group. So now the question is bone the ancestral condition? That is, did all vertebrates originally have bone and some have lost it? Okay? Or is jawless maybe even jawless, that condition is not homologous? Because the idea with hagfish and lamprey is that they're ancestrally jawless. But what if they aren't? What if they actually come from jawed ancestors? Then it gets a little bit crazy. This guy, what do we do with these hagfish and lamprey? And so if you just could ignore hagfish and lamprey, the phylogeny of vertebrates would be so much cleaner. The problem is you can't because they're still alive and just wreaking havoc. I mean, hagfish, they're just kind of being hagfish. But lamprey really do wreak havoc, spreading all throughout the rivers in the Midwestern United States into the Great Lakes, just destroying fisheries as they feed on some of those fish.
Can lampreys easily adapt to different environments?
Oh, man. So lamprey are interesting in that for many of them, the larvae are marine and the adults are freshwater, which is kind of the opposite of what you find in a lot of fishes, where the juveniles are freshwater and the adults are marine. And so lamprey are a little bit interesting. And lamprey as juveniles look a lot like lancelets and actually live a lot like lancelets. But then as they go through that metamorphosis, they start to look a lot more like vertebrates. And so they're just kind of strange animals. To answer your question simply, yeah, because they're kind of built to live in two completely different environments, marine water versus freshwater. Yeah. So Gnathostoma, the jawed fishes, these have a hinge. And so why are they favored? Because they can grab and tear things and jawless fishes cannot. So now you can start to eat something that's even bigger than you are and not just be parasitic, but just to kill it and then slowly chew it up, right? Or eat something that's close to your size. Now you have a much more dynamic feeding strategy. You have a jaw that you can use to grab on to something and to actually tear pieces off. And so that's why jawed fishes are favored, because they can eat a wider variety of stuff. Make sense? Wider variety of stuff. So here are some of our jawed groups. We have an extinct group called the placoderms. These, like ostracoderms, are armored. They've got these big bony plates, but unlike ostracoderms, they have jaws. Very, very clearly jaws. And anyways. Chondrichthyes are sharks, our skates, and our rays. Oh, I'm missing a comma there. That's horrible. That coupled with calling his, verbal outburst a visual effect, you guys have just seen a really bad version of myself. And I'm sorry. You deserve better. That coupled with last week not being able to remember people's names. I mean, it's just, you've got now 2 weeks now of a very bad version of myself. I'm sorry. Because a good version of myself is already not very good. And so when you get a bad version of myself, I'm sorry, you deserve better.
Could you try to give us the better version of yourself by giving everyone an A on the next test?
If you earn it. I don't think giving everybody an A would be a better version of myself.
I tried, guys.
Yeah. So chondrichthyes, the shark, skates, and rays, they have a cartilaginous skeleton. The idea here is that this is kind of a derived condition. They don't have bone, but they would have had to have come from bony ancestors. Okay? And so chondrichthyes, these sharks, skates, and rays, they're just interesting. They usually have internal fertilization, which a lot of fishes have external fertilization. They have placoid scales, which are unique to cartilaginous fishes. The placoid scales are basically teeth all over the body, which is weird. It's really weird, but it works. Have you ever pet a shark, like in a like a tide pool or something? So if you just put your fingers in, you let them swim by you, it feels really smooth. But then if you try to take your fingers and move the other way, it does not feel smooth. It feels like you're basically rubbing your finger across teeth, because that's exactly what you're doing. You're rubbing your fingers across teeth that are covering the entire body. Fantastic. And then they also have these really cool structures called ampullae of Lorenzini, which are able to detect really small electric fields emitted by other organisms.
Is it of or?
Oh my gosh! Another typo. Wow, this is horrible. It's of. I don't want to talk to you. Ampullae of Lorenzini. Ampullae of. Wow. I will put that comma in and I will change that to of, and I will hopefully remember to put it back on canvas because you deserve better. And then our other group, the bony fish. So bony fish make up by far the highest amount of total vertebrate craniate diversity, accounting for well over half. And we can split these into two groups. Actinopterygii, which are the ray-finned fishes. Most fish are like this. And this is in the fins. All there are is bone. There's no muscle in the fin. It's just bone, right? So if you've, I don't know, kept a fish as a pet and you like to take it out of the tank and hold it, right, and pet it, you've felt this. Or if you've gone fishing, you felt the fins, and all that's there is bone. And then you have the sarcopterygians, Sarcopterygii, and these are fleshy finned fishes. Sometimes you'll see them referred to as lobe-finned fishes. It's a horrible name. It's a horrible name. It's one of the textbook uses, but it's better to think about them as fleshy finned. They've got muscles in their fins. Okay? They've got fleshy fins with muscles and just all sorts of wonderful things. All right. I think we're going to end here. I've got a bunch of pictures to show, but I don't have time to get through all the pictures. So we're going to end here. Have a wonderful day. Enjoy yourselves.